this lecture. All right. So, like I said, we talked about second order, and this is where we ended our second order discussion on Friday, talking about iodine and how it follows second order kinetics. Okay, so the next one to talk about then is zero order reactions. Zero order reactions are interesting because they don't pay any attention to the concentration of the starting material whatsoever. So again, our generic formula, A goes to some product, product, you get a free triangle there. As we've seen through all of these, the rate is equal to the negative of the change in concentration of A with respect to time. But the rate law here is a bit different. Because it's zero order, right? It's K times A to the 0th power. Anything to the 0th power is just 1. And so we just end up with the rate is equal to K. So it's a little unusual. We haven't seen that yet, but that's what happens when we have a 0th order reaction. And so we can just, we get out of this that negative change in concentration of A over delta T is K. Just like in all the other ones, we want the concentration of A to be our y-axis. We want time to be our x-axis, and so we rearrange, and we get that the change in the concentration of A is equal to, no change. The concentration of A at any time is equal to that initial concentration, A naught, minus KT. And so we have our graph here. Notice that in order to get a straight line, we don't have to do any natural logs. We don't have to do any 1 over. We just have a straight line, concentration versus time. So talking about half-life, since we spent a good bit of Friday talking about that, right? The half-life here, when the half-life is time, that means, again, this is very similar to first order, that A is equal to A naught over 2. So we have half of our initial concentration at our half-life time. We can rearrange this equation, and we get A naught over 2 is equal to A naught minus K times T1/2. I'm going to subtract A naught from A naught over 2, right? And I end up with A naught over 2 because it's 1 minus 1/2 essentially. And so we rearrange and we get T1/2, our half-life, is equal to A naught over 2, and then we divide through by K. A naught over 2K. So first, second, and zero order reactions, those are the ones that we're going to focus on in this chapter. Like I said, you might see one that's an odd reaction, but we won't deal too much with those. So I wanted to sort of bring everything together, right? We sort of split these concepts. We did first and second order on Friday. We're doing zero order today. And so bringing everything together here. If we have our 0th order, we'll just go we'll go in numerical order, then our rate is just equal to K, right? We don't have to take the natural log of our concentrations. It's just the concentration of A is equal to the initial concentration minus KT. And then our half-life equation, what we just saw, our initial concentration of A over 2K. So that's 0th order. 1st order, the rate is equal to just A times K. I'm sorry. Yeah, A times K. And for 1st order, remember we take natural log. So natural log of A is equal to the natural log of the initial concentration of A minus KT. And this one is the one that doesn't depend on the initial concentration at all. And we just get the natural log of 2 over K. And we said that we can simplify that a bit more if you'd like. That's 0.693 over K. So 0 order, we have no natural log, it's just the concentrations. 1st order, we add in that natural log. And then 2nd order, if you remember, we do 1 over it. So the rate is equal to the concentration squared times K. We end up with 1 over A naught. Sorry, 1 over A equals 1 over A naught. And now instead of minus KT, we end up with plus KT. And our T a half is equal to 1 over K times A naught. Okay. So for the question, it's going to be good to know these equations. They are going to be very useful for you. So that's the 3 types of reaction orders that we're going to talk about. And remember, reaction order, we can determine that experimentally based on the table of data. That's what we did at the end of class on Wednesday last week. Or we can do it experimentally based on the slope of the curve, like we just saw for 0 order, and like we did for 1st and 2nd order on Friday. Okay. All right. So we're shifting gears a little bit. We've talked about how these reactions behave, how these reactions proceed, what it looks like in terms of concentration, how long these reactions take to occur, right? We've talked through a good bit of this kind of stuff. And now we're going to switch gears and talk about the energy required. We're going to talk about how much energy is either required to do the reaction or how much energy comes out of the reaction once the reaction is complete. And so we use this term activation energy to talk about the energy required to get from reactants to products. And so a quick definition here for activation energy. Right? This is the minimum amount of energy required to initiate, to start a chemical reaction. The minimum amount of energy to initiate a chemical reaction. And so for exothermic reactions, remember exothermic heat leaves, exo out, therm heat. So exothermic heat leaves. Overall, the energy is negative. Right? The energy change is negative. This is our delta H. Overall, it goes down, but we have to put in a little bit of energy to sort of get those reactants moving, get those reactants to the point where they actually want to transform from A and B into C and D. In an exothermic reaction, remember this is our delta H, and now it's positive. We have to add in energy, but we don't just have to add in energy, the difference between A and B and C and D. We have to add in enough energy to get it over that activation energy barrier, hump, we sometimes call it, and in order to get over to the products. Okay. Now at the middle here, this AB with the little double dagger, this is an intermediate. And so in this example, what they're saying is that A and B come together to form AB, a new molecule. That's not A, it's not B, it's AB. And then AB breaks apart into C plus D. And so that's the same in both places. Another word for an intermediate is sometimes called a transition state. And so you'll likely hear both of those terms if you look for information out there. Intermediate or transition state, those are interchangeable. You can tell it's sort of transitioning from reactants to products. All right. And so this activation energy, of course, is going to be easier to overcome if we're at a higher temperature, because higher temperatures mean more energy. And so there's some energy dependence on that rate constant. If you had to take a guess, endothermic or exothermic, which of these two has a faster rate constant? Endothermic or exothermic?
Exothermic.
Which of these two barriers is it easier to get over?
Exothermic.
Anyone? Which one has a smaller activation energy?
Can you hear us?
Excellent. Excellent.
Can you hear us now?
Yes, I hear you now. Thank you so much. Yes, exothermic it is. Right, that smaller activation energy means that it's going to be faster for those molecules to convert from A and B over to products than it is for the endothermic. And so those reaction rates, those rate constants, are dependent on temperature, because if we start our molecules with a higher temperature, that means they have higher kinetic energy. And so they might start up here if they have a higher temperature. And so if they start up here, well, then that barrier is going to be lower, and so it's going to be easier for them to get over that barrier at higher temperatures. Right? And so let's take a look at how activation energy and the rate constant are related to temperature. So this is a very generic plot. It's exponential increase, right? And so the equation that we're going to use, the equation that fits this plot, is that the rate constant K, so it's our Y, right? The rate constant K is equal to some constant, or another constant, right? Times E raised to negative activation energy over RT. Okay. And so everything up here is the exponent for E. So what do we have here? Well, K we know is the rate constant. E sub A from our previous slide is the activation energy. What units do energies usually have?
Kilojoules.
Joules, yeah. So we're going to use kilojoules per mole for this one. And so, you know, we're not talking about just a single molecule usually. We're talking about a whole bunch of molecules. So it's easier for us to talk about moles than it is individual molecules. So kilojoules per mole for activation energy. R, remember back to chapters 5 and 6, we had two different values for R. We had the value that dealt with liters and atmospheres in the gas chapter, and the value that dealt with joules in the energy chapter. And so we're going to use that joule version. Right? I call it the energy version. And that's 8.314 joules per mole Kelvin. Something to point out here, just so you're on your toes, the units on R, joules, the units on activation energy, kilojoules, and so we need to be sure that we convert one of those to the other before we solve so we don't have a unit mismatch. And T, of course, is our temperature in Kelvin. A, this is a new term for us. This is called a frequency factor. And this has to do with how frequently the A and B molecules are hitting one another, right? How often do they hit? Not just hit though, how often do they hit in an orientation that will cause them to react? So, for example, here's my coffee cup, and here's my lid for my coffee cup. Right? They can go together a lot of different ways. They can touch each other. You know, this might work, but this is the way that they're supposed to interact with one another. And so it's not just about how often they collide with one another. It's about how often they collide in the right orientation. So that's what that frequency factor is about. For most of what we're going to talk about, we're going to assume that the frequency factor is 1. Right? It makes life much easier if the frequency factor is 1. And so I'll just put here in parentheses, we usually assume that A is equal to 1. And so feel free to assume that unless it tells you specifically in the question what the frequency factor is, or unless the question you're looking at asks you to solve for the frequency factor. Okay. Now, again, chemists, we like straight lines, right? And so this is a curved line. Anytime we have an exponent and we want to straighten it out, we're going to take that natural log. And so if we take the natural log of all this, the natural log on the left is natural log of K. On the right, we get the natural log of A. Now remember, natural log of A, if A is 1, natural log of 1 is just 0. And so that's nice. Plus, well, let me make it a minus because we have this negative sign in front of our E sub A in the numerator, or in the exponent, sorry. Minus EA over R. And I'm going to split the temperature out because look at our x-axis. Our x-axis is temperature. And so again, if we're trying to think about this as a linear equation, this is our y. This would be our b. The negative EA over R is our slope. And then 1 over t is our x. And so this will give us a straight line for that rate constant and temperature relationship. So let's do a quick example. We have some rate constants here for the decomposition of acetaldehyde. And so they're given some rate constants. Those have been measured at different temperatures. Notice this one is the 3/2 order I was talking about we would see later on. It's a little odd for us to see that, but it's okay. So we have some data. We're asked to plot it. I'm not going to ask you to pull up Excel right this minute, but we're asked to plot natural log of K versus 1 over the temperature to figure out the activation energy. Now, I've gone ahead and plotted this, hopefully. Here we go. And so here's the plot of natural log K versus 1 over temperature. We're trying to get the activation energy out, right? That's our question. In order to do that, we need to know the slope, right? So we're going to do our rise over run business. And so M is our slope, right? M is equal to, just as a refresher, negative EA over R. And so the rise in our slope, -4 minus -0.45 divided by our run, 1.41 times 10 to the -3 per Kelvin minus 1.24 times 10 to the -3 per Kelvin. So quick calculation here. We end up with I got M, which again is negative activation energy over R, is equal to negative 2.09 times 10 to the 4th. Now, units here, top doesn't have any units, right? The bottom is 1 over Kelvin. And so divided by Kelvin means Kelvin is now in the numerator. And so our units here are Kelvin. Okay. So that's the slope of this line. Now we know R, and so we can plug all this in. Negative 2.09 times 10 to the 4th Kelvin is equal to negative activation energy divided by 8.314 joules per mole Kelvin. Multiply both sides by 8.314. I'm going to go ahead and divide through by that negative. And so I get 174,000 joules per mole is equal to my activation energy. I want this in kilojoules per mole rather than in joules per mole. And so I end up with 174 kilojoules per mole. So if you're given data, you can plot it. Just make sure that you take the natural log of the rate constant and 1 over the temperature, and then use that information to figure out activation energy. Any questions about how to solve that? All right, so that's one way to use this equation that we saw. By the way, let me just point out here, this equation that I gave you has a name. This is the Arrhenius equation. Don't worry, I won't ask you to spell it. But this is the Arrhenius equation. And this is just one way for us to look at it. Right? The other way for us to look at it involves difference in temperatures and how those temperatures can change the rate constant. Okay, so let me go back to where we were. Right, so here we're looking at a different way of writing the Arrhenius equation where we have two temperatures. Right? So two temperatures, the activation energy doesn't change. Right? Activation energy is not changing. It's just how many of those molecules have enough energy to get over that activation energy at a given temperature. And so with a change in temperature, we can figure out the change in the rate constant. Right? Our textbook prefers this version on the bottom. It really doesn't matter to me which one you use. They are identical. One is just combine the denominator into like terms. It's really up to you which one you prefer. But for now, I'm going to run with the top one. The top one to me seems like less work. And so I'm going to put the top one and we're going to solve a quick problem with it. What's the rate constant for a first order reaction? It's 3.46 times 10 to the negative 2 seconds at 298 K. And we want to know the rate constant if we increase the temperature from 298 to 350. Okay? This is not a huge increase. This is not even up to the boiling point of water. But we are, we're just about, we're going to use the Arrhenius equation to figure this out. And so natural log, we need that two-term equation. So I'm going to write it out first, and then we'll start plugging stuff in. Equals activation energy over R, 1 over T2 minus 1 over T1. Okay. Now let me go in and label some things, right? We have a rate constant, right? We have a temperature. It really does not matter one tiny bit which one you choose to be rate constant 1, which one you choose to be rate constant 2, as long as you make sure you match the temperature with it. Right? And so if this is going to be K1, then this has to be T1. Right? We have another temperature here, that must be T2, and we have an activation energy, EA. So the only thing we don't have is K2. That's what we're solving for. So natural log of 3.46 times 10 to the negative 2 divided by K2 is equal to, I'm going to go ahead and convert this to joules rather than converting R to kilojoules. Again, you could do it either way, convert R to kilojoules or convert your activation energy to joules, but one of those two has to be done. All right, my second temperature, 350. My first temperature, 298. Yeah. So, do a little algebra. When you're done, tell me what K2 is equal to. All right. So I mentioned sort of the tail end of lecture on Friday that if we increase temperature, we're going to increase how quickly our reaction goes. And so that's, again, because the higher kinetic energy means they're going to collide more often, means that they're going to react more frequently. So that rate constant is going to go up. And so since we're increasing our temperature, we expect our K should be larger than 3.46 times 10 to the negative 2. Who has a good answer for K2 that's larger than 3.46 times 10 to the negative 2?
I don't know if this is right, but I got 0.702.
Excellent. 0.702. Because we're not changing the order of our reaction, the units are still the same. 0.702 per second. Excellent. Okay. Right. Just a quick reminder to get rid of that natural log. Remember, we raised everything to the power of e to the power of everything. And so that's how you get rid of the natural log part. So K is 0.702 per second. Absolutely. Okay. Now I mentioned, excuse me, I mentioned that that A factor, that frequency factor, is important, and that's important because in order to react, they have to be pointing in the right direction. So in this example, we have carbon monoxide reacting with nitrogen dioxide, and if those two react carbon to oxygen, then we'll get a reaction that carbon monoxide will steal an oxygen. However, if we orient it so the carbon and the nitrogen bump into one another, we won't get any reaction, right? We call that an ineffective collision. And so that frequency factor sort of takes into account how many of the collisions are effective and actually lead to reaction occurring. All right. The last part of chapter 13 talks a little bit about breaking big reactions down into their smaller pieces. Okay, we call those smaller pieces elementary steps, or sometimes elementary reactions. But these are sort of the individual steps in a reaction. Right? And so these elementary steps represent progress toward an overall chemical reaction. These are supposed to be, they're simpler than our overall reaction. And so that's why we call them elementary, right? A reaction mechanism is the sequence of steps, the sequence of these elementary reactions that lead to the overall reaction. And so we need to know not only what the steps are, but we need to have them in the right order. Right? Remember, we talked about how you can have those intermediates, and if you make an intermediate in one step, you have to make sure that that intermediate is used up in the next step. Otherwise, it's a product rather than an intermediate. And so we need to know not only what the elementary steps are, but also what the order of those steps is. And so, for example, if I have 2 nitrogen monoxide and I react it with oxygen, well, you can go in a lab and you'll do this and you find that you get NO2, you get 2 molecules of NO2. However, if you're doing this in a lab, you might discover that during this reaction, you get a little bit of N2O2. You detect a little bit of N2O2. N2O2 is not a reactant. N2O2 is not a product, but N2O2 must be one of our intermediates. And so if that's true, then that means that it has to be the product of a first elementary step. So N2O2. So I'm going to write over here, let me change colors. I'm going to write over here that intermediates must be a product in an early step and a reactant in a later step. Okay? Because those intermediates have to get used up, we have to make them at some point early in the overall reaction. I have to use them up later on in the overall reaction. And so based on these reactants that we have, NO and O2, the only way to get into O2 is to combine those two NO molecules. Right? And so it must be that this first step is NO plus NO. Right? That's going to lead to N2O2. And so that's step one. So step two, okay, we're going to use up our N2O2. Now, I've already used my NO for my overall reaction. The only thing that's left is O2, so that must react. And that's going to form my 2NO2. Now, it's super important that you make sure everything stays balanced. You make sure that you're getting rid of your intermediate in your overall reaction step. And so if we add these two reactions together, I end up with 2NO, 2NO. Now I've got an N2O2 as a product and an N2O2 as a reactant, and so it cancels out. All of your intermediates should cancel out like that. I'm left with O2 as a reactant, and the only product I have, 2 molecules of NO2. Now that matches our overall reaction. And so we're fairly confident that those two elementary steps are the only steps present in that reaction mechanism. And so, you know, the words that they use to tell you there's an intermediate can vary a lot, right? N2O2 was detected in the reaction. That's their way of telling you, hey, by the way, there's an intermediate. That intermediate happens to be N2O2. It could sort of just come out and say that there is an intermediate and here's what it is. It could tell you that a colored compound was formed and tell you something about that colored compound so you know the formula of it. And so that overall reaction must look something like this, where those two NOs have to combine. Again, their orientation matters because they must combine nitrogen to nitrogen to form N2O2. And then that N2O2 reacts with oxygen molecule to form 2 molecules of NO2. Now, it could be that that last one actually is 2 more steps. You know, you end up with NO2 plus an O floating around. I don't really know. This is what they have told us. All right. So talking about intermediates and trying to figure out what intermediates are. And so these intermediates are chemical species that appear in a reaction mechanism, but not in the overall equation. So these are species that happen to be formed during a particular chemical reaction, but they're not there at the beginning and they're not there at the end. They're used up. So like we saw earlier, the N2O2 is a good example of that. When we talk about intermediate reactions, or elementary reactions, elementary steps, we're going to talk about the molecularity of that reaction. That tells us something about the number of molecules that react. Usually we don't talk about this for our overall equation. We only talk about it in the elementary steps. Okay. So unimolecular, well, I bet you can guess. There's only one molecule reacting. And so unimolecular, there's only one molecule, only one chemical species reacting. Usually, if it's one molecule reacting, right, it's got to be a decomposition process. Now, one molecule is splitting up into smaller molecules. Bimolecular, of course, 2. Intermolecular is 3. Okay. All right. The last thing before we head out today, you know, how do we know if it's unimolecular, bimolecular, right? So an example here: A going to some products. For bimolecular, it could be two sort of reactions. It could be A reacting with itself, or it could be A reacting with B to give us some products. Both of those are bimolecular reactions. It's not necessarily two different molecules. It's just two molecules reacting in order to be bi or termolecular. Now, remember, in order to react, these things have to collide with one another. And so termolecular reactions are pretty rare because you have to get 3 molecules that all collide at exactly the same time. Quaternary reactions, where we have 4 molecules colliding at the same time to react, are almost unheard of, right? They don't really exist. And so we're not going to talk about them. And so here are some rules for writing plausible reaction mechanisms. And you have these in your notes. The overall elementary steps have to give the overall balanced equation. Right? So just like we did with the N2O2 example, we added up those elementary steps, we crossed out the intermediate, and we got back our overall reaction. Okay? But since we're talking about kinetics, the reason we're interested in these reaction mechanisms is that it turns out the single elementary step that's the slowest is the elementary step that determines the rate for the whole reaction, right? Sort of you're as weak, your chain is only as strong as its weakest link, right? Same thing, a reaction is only as fast as its slowest elementary step. And so the rate determining step is the slowest elementary step. In a reaction mechanism. Okay. All right. When we start lab today, we'll probably do this last example that you have, example 10. We'll probably do that right before we jump into our actual lab experiment, just so we can tie the knot on this chapter 13 material. Okay. All right. Stick around if you have any questions. If not, have a good Monday. I'll see you at 2.
Thank you.
Thank you.
Thank you.
Thank you.